Our team, When Can You Guys Meet Up, focused on improving the efficiency of the installation of solar panels for Sunrun's last mile install. We will be covering the inner working of our model. These details include input analysis, assumptions, modeling approach, verification and validation, output statistics, optimization, and results and recommendations.
Our team input the data from the Excel file into the JUMP software to fit distributions for the arrivals per day, the job processing times, distance to each job site, and the number of panels used for each job. We used Excel formulas to count the number of panels per day and the hours spent at each job. For the distance, we assumed that such a small area of the world's hemisphere would allow us to use the Pythagorean theorem to get a rough distance from the warehouse to the job sites. And finally, we were given the panels per job in the data. Shown here are the distributions we got for each data set. Here are a few assumptions we made for our model. The first scenario, the jobs will arrive at 7 a.m. every morning. Work day is from 7 to 3 p.m. Any time worked over that will be considered overtime. The trucks travel at 40 miles per hour. We will allocate one electrician to each job, and contractors, of course, will not count as installers. Approaching our model, talking about the arrival process, it will arrive on a timer, like we said, at 7 o'clock every morning, and that number will be pulled from the distribution we talked about above. The state variables that we will assign when these entities arrive, we will assign each entity a number of panels using an add-on process, and the entities their picture will change according to the size job being worked. As you can see here, we have one source where each entity will flow through, and it will arrive at the facility loading area. If the entity cannot seize all of the resources it needs, it will go to the dummy server and wait until the next day. Once the entities or the jobs have been loaded up, they will head to their servers where they will begin processing. The paths to the servers we set each at 100 miles so that we could scale the speed of the entity to mimic our travel time. Our servers will use a work schedule, so they will all shut off at 7 p.m. If a job is still there, however, they will finish that job that is being worked. And what we've done is we've created a if statement that will allow us to take the ratio of the total number of workers available that we would like to have on our crew, and we will divide that by the crew that we actually seized, and that will give us a ratio that we can multiply times our distribution. So if we don't have enough crew to fill out completely, then the processing time will take a longer amount of time to complete the job. For our resources and our crew, we will have one resource represent each worker type or employee, and the capacity we will set using a work schedule for these resources. And you can see how we have used cost multipliers as well to pay them overtime for any hours they are working outside of 7 o'clock to 3 o'clock.
The first scenario requires a number of add-on processes throughout the model. Right when an entity is created at the source, a random number of panels is assigned as a state statistic. This will determine the size of the job. At the loading facility, if more than 5 entities are backed up before 7 a.m. when all the jobs are sent out, those entities are sent to a dummy server to wait until the next day. This prevents workers being seized overnight. An install blocker process takes 5% of entities and sends them back to the loading facility, sets a delay to unload the vehicle, adds the number of driving miles, then releases all workers for the day. These are implemented at each of the work sites. A system exiting process decides whether or not the entity seized an electrician or a contractor, then releases all the workers. This is implemented at the sink. This add-on process seizes the correct number of workers based on the size of the job. It is implemented as the entity enters the loading facility. First, the process decides if it is a small, medium, or large job. Here we have shown the small job, but the medium and large jobs look exactly the same and are executed based on the first process, as you can see. It then assigns a random speed and distance which the entity must travel. Next, it decides if there are enough of each worker available to perform the task that day. If not, it waits in the dummy server. Some resources require special process attention, such as seizing a contractor instead of waiting if there is not an electrician available. For Scenario 2, the modeling approach is similar to Scenario 1 with some major differences. This time we are sending all the equipment to the work sites prior to workers starting the job. This is aimed to save worker time. In this model, the entities represent the equipment being sent to the work site for the job rather than the actual job itself. One source creates the entities. From the start, 15% of work sites do not have the real estate to keep an equipment pod, so those jobs just essentially go through the Model 1 scenario. The travel logic this time is different. Paths have zero length, and the entities are picked up at the loading facility by one vehicle of negligible speed. The distance is assigned in an add-on process implemented at the loading facility. This vehicle used in the scenario belongs to a contracted company that provides pods that send out equipment. The vehicle can carry up to 5 equipment pods in one trip, dropping them off at work sites. The distance this vehicle must travel is decided by the add-on process shown below, pulled from the previous data. The crew is seized using the same add-on process as Scenario 1, however there are some minor changes. Instead of leaving from the facility on a work truck, the workers can now just drive to the work sites on their own. However, this would not be totally fair to the workers to pay for their own travels, so each receives a fixed gas stipend of $50 each week. The crew is seized using the same add-on process as the first scenario, but the process is implemented at the work sites instead of the loading facility.
To validate that our model was operating as expected, we made use of some of Simio's built-in features. Status labels were useful for watching the model run in real time to confirm that resources were being seized by each entity passing through the system. Breakpoints were helpful when letting the model run until it encountered a specific condition in the model logic. For example, when an entity's token reached the seize foreman step within the process. At that point, we utilized the trace feature to follow exactly how the process logic was being evaluated. This made it incredibly helpful to track jobs of different sizes and verify that they were seizing the correct size of crew.
In order to track wait time for customers, we created a tally statistic and added it to the exit system process as a tally step that records the time in system for an entity once it enters the sync. Model entity states track the number of panels and distance traveled by a specific entity, and once the entity leaves the system, the model states update to account for the panel and mile additions. These states were consolidated into output statistics to then be viewed as responses in the experiment window. The only difference in output statistics between Scenario 1 and Scenario 2 are in the distance traveled cost formula. Scenario 1 updates cost as the entity leaves the system, multiplying the mileage for that entity by 2.35 to account for the company equipment and box truck assumed per entity. Scenario 1 updates cost as the entity enters the system, multiplying the assigned mileage by 4.10 to account for a weighted average of container and mileage cost. In Scenario 2, 15% of the homes have to use Scenario 1 exit process pictured here, while the rest use the process without the assigned distance cost, because it was already assigned at the beginning. The output for customer wait time was created by adding 3 separate responses, one showing average, maximum, and minimum. Resource costs were totaled by adding responses that pulled directly from their usage cost charge, and travel costs pulled from the output statistic value originally mentioned before. Finally, cost per panel was calculated by summing the individual resource costs with the travel costs, and then dividing that number by the total number of panels.
In order to make a recommendation to Sunrun for what changes to consider making to their operations, we used the OptQuest add-in feature in the Simio experiment. First, we had to create reference properties for setting the small, medium, and large crew sizes. Then we established upper and lower bounds for each parameter. Our group chose to use the experiment property for multi-objective weights for establishing an optimization objective. Based on Sunrun's stated desire to decrease the time between permit approval and job completion, the responses for average customer wait time and the total number of panels were chosen, with wait time receiving more weight than the total number of panels. Our analysis can be summarized with the recommendation that the pod scenario, Scenario 2, having a significant impact on the throughput of Sunrun's operations, with nearly triple the number of panels installed in 1 year, while reducing the total time between permit approval and job completion.